Hello, welcome to the ASME Pressure Vessels and Piping Virtual Conference from 2020. This is paper number 21003. Topic here is validation of the new gamma exponent model for axial crack assessment in oil and gas pipelines. My name is Colin Scott. I'm an independent contractor out of Calgary, Alberta. This is a project I've been working on for about a year and a half or so. Hopefully wherever you are, you're comfortable with a cup of coffee in your hand, or if you're like me or it's after 5 o'clock and you don't have coffee in your hand, I'm pretending it's after 5 o'clock. First of all, I'd like to say that this work was funded in part by IRIS NDT Engineering Services out of Calgary, Alberta. For the outline, I'm going to give you a quick recap of the original log secant model for surface breaking axial cracks. And specifically why I do not like the model. I know that this is a 50-year-old model that appears dated. There are a lot of folks that don't like it too much. I'm going to tell you where I think the limitations are. And that's an important thing because the new model that I've developed, the gamma exponent model, actually builds on that original log secant model. I'll tell you what I've changed and why I've changed it, and hopefully why I like it a lot better. Then we're going to look at some industry data validation and statistics. So if you look at the original log secant model here, this is the model in what I call sort of the unfolded format. Sometimes you'll see it in a slightly different format, but it's really just how you're packaging the mathematics. So starting from the left-hand side, we have the predicted failure stress divided by the flow strength. And then we have our A over T is going to be our flaw depth ratio, so with respect to the wall thickness of the pipe. Looking over at the right-hand side, we have an arc cos and exponential term. The K mat is going to be our toughness of our material. The C is going to be half of our crack length. And then I guess also on the left there, we've got the folius factor buried in that ratio term. The folius factor is a function of the length of the crack and the diameter and wall thickness of the pipe. Now, those of you that are experienced with this model will know that we can look at the left-hand side of that chunk of the equation, and that's really the same form as ASME B31G that's used for corrosion. I'll get to that a little bit later, but that becomes quite an important thing from my perspective. Now let's take a much closer look at this. If you look at the original log secant model, it was actually derived for through-wall flaw. When you look at all the whole section of the model that I've got in light blue there, this is all theoretically and mathematically derived based on a through-wall crack. The developers were originally worried about a leak rupture boundary. So you see the C in there, the arc cos exponential term with a C, that's theoretically based on a through-wall crack length. And then when you look at the M, the folius factor, that's also based on a through-wall flaw. So the original incarnation of this model was to look at a leak rupture boundary. The developers then added the section there I've shown in pink, which is an empirical correction, which basically takes a through-wall crack model and turns it into a surface breaking crack model. Now, when you think about this, you've got about 80% of this whole model is theoretical and mathematically based on crack length. For surface breaking flaw, that's not really the balance that we would like to see. We've only got about 20% of that pink section of the model that is looking specifically at the crack depth. So I think that there's a bit of a problem right there. Now, those of you that are also familiar with the model will know that this model tends to be overly conservative. My model shows that it's about 14 or 15% overly conservative. And my personal feeling for why that is because we've got too much focus on crack length. And too much focus on crack length means that all of the predictions are being skewed in the overly conservative direction. Now, I think that the developers recognized that fairly early on, and they came up with a correction factor, or a modification factor, in the 1990s. And that modification factor was in the form of a depth ratio. I think that that was helpful in that it lined up the numbers a lot more accurate, but it didn't really necessarily fix the underlying problem that I see with the model. Now, what I ended up doing is recognizing that if the original model was based on a through-wall crack, and that's based on crack length, and then afterwards empirically corrected for depth, why don't we try doing that same approach, but in reverse. We start off with a part through wall crack, assume it's infinite length, go through all of the math the same way that the original model was done, based on a strip yield solution, and then see where we stand, and if necessary, come up with an empirical length correction. So that's what I did, and I ended up landing on this form of equation, which I've nicknamed it the gamma exponent model, or the GEM. So just like before, we have a predicted failure strength divided by a flow strength. Rather than having the typical B31G term, I've got that remaining ligament to the power of gamma exponent. When you look at the Arcos exponential term, there have been a couple of changes there. One is we no longer have an 8 factor, we now have a 10 factor. And in order to understand that, you've got to dust off your fraction mechanics textbooks and realize that a surface breaking flaw will have a correction factor on the stress intensity of 1.12. And then when you go through the derivation, that ends up getting squared. So you end up with 1.12 times 1.12 times that 8 factor ends up with pretty close to a 10 factor with a little bit of rounding off. And then also within the Arcos exponential term, we have A, which is our crack depth, rather than before we had C, the half crack length. The gamma exponent for the crack model here is the length of the crack divided by the radius of the pipe, and it's limited up to a value of 1. So that's where we stand with the new model, very similar format to what we'd actually seen before. And as I developed this model, it also occurred to me that I could probably take out that initial chunk and see if that works for a corrosion model. Now, if you take a look at this, we now have bits that I've highlighted in blue here. All of these parts are actually theoretical, mathematical, and based on a part through wall crack. So now, rather than having a real focus on length, here we've got a real focus on depth. And in my mind, that's a much better approach from a mathematical perspective. Now, I wasn't able to come up with a great way to accommodate the length, and so I came up with a semi-empirical length correction factor in terms of that gamma. My hope, though, is that the whole model is balanced a little bit better mathematically. So there is some fine print on this model. The flaw depth can be modified by a pi/4 factor for a semi-elliptical profile. And then another thing is that I use a 0.88 correction factor for my stress corrosion cracking shielding effects. The factor that I came up with is still a work in progress. It needs a little bit of refinement, but it is based on some classical solutions. The K-mat, the toughness that I'm used for the validation, is the lower bound Wallen-J Sharpie correlation that some of you might be familiar with from API 579. I'll say that the Sharpie over area correlation that's often used in these models is not recommended. I'll say that there are probably a lot of viewers out there that have read Dr. Ted Anderson's PRCI report from about 3 years ago, where he was looking at various models. And what he recognized was that the Sharpie over area correlation is about 10 times higher than the Wallen-J correlation or the Novak-Rolf correlation that some of you will be aware of. Now, if you stop and think about it, hypothetically speaking, and this is partially guesswork, if the Sharpie area correlations were done under plane stress conditions and the Wallen-J correlations were done under plane strain conditions, then you would expect there to be about a 10 times difference in those values. And then if you take that thought process a little bit further, I mentioned that the original log secant model was actually based on a through wall crack. And if you think about a through wall crack and the crack tip in the length direction, that crack tip is going to be under plane stress conditions, right? So you're going to see a higher apparent toughness. When you switch over and you go to a surface breaking crack, where your crack is embedded halfway through the wall thickness, in that case you're going to be under plane strain conditions. So you're going to have a much lower apparent toughness. I'll leave some of you to chew on that for a while, because that actually is very important when you dig around in the nuts and bolts of the equations. I'm using a flow strength of the yield strength plus 69 megapascals or 10 KSI. That's pretty standard. I did not mess around with that with any of the other options. I'm assuming thin wall pipe with a diameter over wall thickness ratio of 20 or more. Then I'll also mention that when I start working with the gamma exponent model for metal loss or corrosion flaws, I actually limit the gamma exponent to 1/2. And I know that that's going to cause some of you out there a lot of heartache, because what it means is that the remaining strength then varies, or the remaining strength converges, I'll say, as you get a longer and longer corrosion flaw, to the square root of the remaining ligament. And that sounds completely crazy to most of you. There is a technical rationale which I have put together in an ASME journal that I can certainly you can certainly look at later on. I know that that's going to cause you some concern, though. I've managed to compile quite a bit of validation data. A lot of this will be work that some of the readers and viewers will have seen before. I have 106 crack-like flaws, and that's a combination of lab work, long seam weld failures, and stress corrosion cracking failures. I also have 85 metal loss data points from AGA 5th Symposium in 1974 and Cronin's doctoral thesis of 2000. So the grand total is I've got 191 data points. In each one of these cases, we have a data set that includes a pipe diameter, a pipe wall thickness, a yield strength, a toughness, and a crack length, crack depth, and an actual failure pressure. So we can go through the exercise of figuring out how well the model is working. So here's a validation plot with all of my crack data. And on the y-axis, we have the predicted failure stress, and that's predicted using the GEM model. On the x-axis, we have the true measured failure stress. And so ideally, all of our data points would lie along that 1-to-1 ratio. But that's not the case. We always expect to get a little bit of scatter. That being said, things look pretty good. We do have some data points that are in the upper left quadrant, which is non-conservative. So these are problem features that represent possible safety issues. We also have some data points that are to the lower right, and these are overly conservative predictions, which means that we might be digging up pipe and doing repairs on pipe that really doesn't necessarily need it. You'll see in the top title block there, I've got a ratio of 0.98 listed. So that's the ratio of the predicted failure stress divided by the true failure stress. So long story short is that the model is overall, on average, it's about 2% overly conservative. And we've got a standard deviation there of 0.18. Now, one thing that I should mention here is that I'm a believer that when we're doing validation models like this, we should be using all of our true properties, and we should be targeting a ratio of 1, meaning that we've got ideal accuracy. There's some people that will argue that you should have a conservative model, and I don't agree with that. I think that if you have a conservative model, but you don't know why it's conservative, then you're really just putting some inaccuracy and uncertainty into your integrity work. My preference is to go for an accurate model and a precise model, and then after that, you can apply conservatism such as using a lower bound yield strength, or if you like, you can add a tool tolerance. That's obviously up for debate, though. If you take a look at the statistics, in this case, I can separate out the laboratory tests, the long seam failures, and the stress corrosion cracks. The laboratory tests and the long seam failures, on average, are pretty accurate. When you look at the standard deviation, you see that the long seam failures, they're a lot less precise. It's a lot more scatter in the data, in part due to the variability and toughness along the long seams. It's going to be a headache for most analysts checking their models. When it comes to the stress corrosion cracking, I've got an overly conservative model by about 14%. That really tells me that I need to do a little bit more work in refining that 0.88 factor. You'll see on the right side of the table, I've got the COV listed here. That's a statistic that you're going to see in a lot of the other papers that people have done, and they use that as a measure of precision. I'm not a particular fan of that one because the way it's calculated is the standard deviation divided by the average, and what that means is that that value, although it appears to be a test of precision, it actually gets skewed by the accuracy of the results. So I like to avoid that. Now, a lot of work has been done on various other models with various other data sets. I've discussed those a little bit in the actual paper, which you can find in the conference proceedings. I'm not going to bore you with all of that right now. But I will say that the accuracy of 0.98 and standard deviation of 0.18 lines up very well. I'm not aware of a data set that's quite so large and varied that comes up with a combination of accuracy and precision that's as good as this. You know, everybody's going to be curious to see how the gem lines up with the various other models. I think it lines up very well, but I'll leave you all to look at the numbers. When you look at all the other models that are available in the market to do similar types of things, I'd like to point out that all of these industry models include some sort of combination of that NG18, the ASME B31G form of the equation, or the strip yield models that we discussed earlier. And so, you know, any misgivings I've got about that original log secant model, quite frankly, they apply to all of these other models, which are in their own way going to be sort of mathematically skewed in very similar directions. Here I've got a plot of some of the deeper flaws. These are all of the 80% through walls. Some of the model developers will ignore these deep flaws, and the basis for most of the pipeline operators is that these represent leak threats that would be dug based on their depth, and so knowing what the failure pressure of them is isn't super important. I think it's important to look at them to make sure that the math is doing what we think it should be doing. Here's a plot where I've included the metal loss features, and as I mentioned, when I'm using the gem for metal loss, I'm just taking a look at that remaining ligament term to the gamma exponent. And in this case, I mentioned that I've limited that gamma exponent to 1/2, which means that the remaining strength is converging to the square root of the remaining ligament. That's going to give a lot of you heartache, but if you look at it, it actually does line up fairly well. The overall accuracy and precision of this data set with 191 points is a ratio of 0.97 and a standard deviation of 0.16, which lines up fairly well. So in summary, I've told you a little bit about the original log secant model and how it's theoretically derived based on length of a through wall flaw and then empirically corrected for a surface flaw. I think that leads to some mathematical wonkiness, I'll say. And so what I've done is I've gone back to the drawing board and rather than zigging, I've decided to zag and come up with a very similar model, but based on depth of a surface breaking flaw and then empirically corrected for length. And you saw from the preliminary validation statistics look to be quite encouraging. That's both for cracking and corrosion flaws. If any of you are interested in learning any more, please dig through the conference proceedings. You can find this paper in written form, and it's got a few other bits and pieces in it that I haven't mentioned here, so please help yourself. The second one I'd like to mention is I did a similar paper for the NACE conference, North Area Western Conference in Regina. And with that, what I'm doing is I'm focusing on corrosion assessments. What I do is I take the B31G equation and I basically turn it inside out and demonstrate that from a mathematical perspective, the Fullius factor approach does not work for surface breaking flaws. And then finally here I've got a journal paper, ASME Journal of Pressure Vessel Technology. This one is some hardcore math. It's not for the faint of heart. So if you're interested in all this stuff, please jump into it, but it is not quite the easy read that other papers will be. So if you've made it this far, thank you very much for your attention. I think that there's going to be a Q&A session through the conference somehow, but I'm not sure how that works. If you do have any questions, you're certainly welcome to find me through LinkedIn. Thank you very much for listening. Hopefully everybody's learning a lot from the conference and getting through COVID crisis okay. Thank you for your time. Have a good day. Bye.